A pipeline serving a regional emergency management office runs clearly for 4 months. Response quality is consistent, users trust it, then hurricane season arrives. The quality patterns shift dramatically. Users are asking about wind damage, storm surge, and coastal flooding at volumes the previous months never produced. The retrieval layer was tuned against a balanced query distribution. It was never optimized for the concentrated volume of coastal event queries that hurricane season generates. Similarity scores on coastal flood chunk retrievals are lower than the baseline established in Part 19. The pipeline is not broken. It is operating outside the conditions it was evaluated against. Without monitoring infrastructure that detects the input distribution shifts, nobody knows until the emergency management director asks why the pipeline keeps returning incomplete answers about storm surge events. Monitoring does not prevent the shift. It surfaces it in time to do something about it. This is Keeping It Honest. Production Monitoring and Drift. Models Part 20. A pipeline that was working last week may not be working the same way this week. Here's how you know. Section 1. What can drift in a language model pipeline? Drift is the term for any change in the statistical properties of the data or behavior of the system that was not present when the quality baseline was established. 4 drift types apply to the NOAA pipeline specifically. Number 1. Input drift occurs when the distribution of incoming queries changes meaningfully from the distribution used to evaluate the pipeline. The quality baseline in Part 19 was built against a representative sample of the queries the pipeline was expected to receive. When real usage diverges from that sample, the baseline metrics no longer accurately predict response quality. The hurricane season scenario in the opening is the input drift. The queries changed, the pipeline did not. Number 2. Retrieval drift occurs when similarity scores and retrieval patterns for a stable set of queries changes over time. This can happen when new documents are added to the corpus, changing the vector space neighborhoods that determine when chunks are nearest to a given query vector. It can also happen when the serving infrastructure changes in ways that affect embedding generation consistency. Retrieval drift is detectable by running the same test queries from Part 19 against a live pipeline periodically and comparing the retrieved event ID against the baseline retrieval results. Number 3. Response drift occurs when the pipeline produces responses that diverge from the quality baseline metrics established in Part 19 without any change in the retrieval layer. Response drift is typically caused by changes in the model's behavior, which can occur when the baseline model is updated, when the adapter weights are replaced, or when the prompt changes alter the model's output behaviors in ways that were not anticipated. Number 4. Data drift occurs when the NOAA corpus itself changes in ways that affect pipeline behavior. New annual data ingestion is the primary source of data drift for this pipeline. A corpus that gains 200,000 new storm events covering a new year will have different vector space density in regions of the embedding space that correspond to the new data, affecting retrieval patterns for queries in those regions. Section 2. The monitoring stack. The monitoring infrastructure for the NOAA pipeline has 3 layers that each address a different drift type. Number 1. The evidently layer monitors input distribution and data drift. It compares the statistical properties of incoming queries and retrieved chunks against the baseline distributions established during the evaluation phase and alerts when distributions diverge beyond configured thresholds. Number 2. The quality metrics layer monitors retrieval drift and response drift. It runs the automated evaluation suite from Part 19 on a scheduled basis and compares current metrics against the quality baseline thresholds. This layer already exists as the prefect flow built in Part 19. The monitoring article extends it with alerting and trend analysis. Number 3. The infrastructure layer monitors the serving stack health. Token consumption, request latency, queue depth, GPU memory utilization, and error rates are the operational signals that indicate infrastructure problems distinct from the model quality problems. A spike in request latency that coincides with stable quality metrics indicates an infrastructure problem. A decline in quality metrics with stable latency indicates a model or data problem. The 2 layers together localize failures in the right part of the stack. Section 3. Building the stack. The 5 steps that follow build each layer of the monitoring stack in sequence. Step 1. Input distribution monitoring. Cloud Code prompt. Write a Python monitoring script using Evidently that tracks input distribution drift for the NOAA LLM pipeline. The remaining prompt can be seen in the Substack article. You are asking Cloud Code to build a daily input distribution monitoring pipeline that detects when the queries arriving at the pipeline are diverging from the distribution the system was evaluated against. The 30-day trend function is what distinguishes a one-day anomaly from a sustained shift that requires action. Success is achieved when the daily drift report runs against the API JSON log and produces an HTML report. Artificially injecting queries about the topic not represented in the test dataset, coastal flooding events, for example, produces a drift score above the moderate threshold. The trend function returns an increasing trend after 3 consecutive days of elevated drift scores. Step 2. Retrieval drift monitoring. Cloud Code prompt. Write a Python retrieval drift monitoring script that runs weekly against the NOAA LLM pipeline and detects changes in retrieval behavior from the quality baseline. The remaining prompt can be seen in the Substack article. What you're asking Cloud Code to build is a weekly retrieval drift detector that catches changes in which documents the pipeline services for known queries. The corpus change detection function is the mechanism that connects new NOAA data ingestion events to retrieval drift monitoring. When new annual data is added to the corpus, the retrieval drift monitor should run immediately rather than waiting for the weekly schedule. Success is achieved when the weekly report runs and produces consistent results against a stable corpus. Adding new NOAA records to the vector store triggers the corpus change detection flag. A query that previously returned a specific event ID as its top result, but now returns a different one appears in the retrieval shift event log. Step 3. Response quality monitoring. Cloud Code prompt. Extend the weekly prefix evaluation flow defined to increase response quality trend monitoring. The remaining prompt can be seen in the Substack article. You're asking Cloud Code to build a trend-aware quality monitoring layer that distinguishes between a pipeline that is currently below threshold and one that is heading towards threshold. The degrading status is the early warning signal. A pipeline flagged as degrading gives the operator time to investigate and intervene before the critical threshold is crossed. Success is achieved when the weekly flow produces a quality trend log entry after each run. Artificially reducing response quality by modifying the system prompt produces a degrading trend signal after 2 consecutive weekly runs. Restoring the original system prompt reproduces a recovering trend signal in the subsequent run. Step 4. Infrastructure monitoring. Cloud Code prompt. Write a Python infrastructure monitoring script that tracks the operational health of the NOAA LLM pipeline serving stack. Every 5 minutes, collect the following metrics from the pipeline's running processes. Request latency in milliseconds. The remaining prompt can be seen in the Substack article. You're asking Cloud Code to build a 5-minute interval infrastructure health monitoring that tracks the operational metrics that distinguish infrastructure failures from model quality failures. The alert thresholds are conservative starting points calibrated for minimum viable hardware. Adjust them based on the normal operating range observed in the first 2 weeks of production operation. Success is achieved when the infrastructure log accumulates entries every 5 minutes. Simulating a slow response by introducing a delay in the pipeline triggers a latency alert. The daily summary produces accurate aggregates from the data log. The GPU memory alert fires when memory utilization is artificially elevated by loading a second model alongside the pipeline. Step 5. Consolidated alert dashboard. 4 monitoring scripts producing 4 separate log files create an operational picture that requires reading multiple files to interpret. A consolidated dashboard that surfaces active alerts across all monitoring layers gives the operator a single view of pipeline health. Cloud Code prompt. Write a Python dashboard script that reads the 4 monitoring logs and produces a consolidated pipeline health report as an HTML file. The remaining prompt can be seen in the Substack article. You're asking Cloud Code to build a self-refreshing HTML dashboard that consolidates the operating picture from all 4 monitoring layers into a single view. The plain text summary function is what makes the dashboard's output visible in the system's journal alongside the other pipeline process logs. Success is achieved when a browser shows current pipeline status with active alerts and trend charts. The file refreshes every 5 minutes with current data. Triggering an alert in any monitoring layer causes it to appear in the dashboard within the next refresh cycle. The plain text summary output appears in the system journal log. Section 4. When to act on what monitoring tells you. Monitoring produces signals. Signals require interpretation before they require action. 3 response levels map to the alert categories the monitoring infrastructure produces. Number 1, a moderate drift signal or degrading quality trend warrants investigating before intervention. Pull the detailed drift report. Identify which query categories are driving the drift and determine whether the shift reflects a genuine change in user behavior or an anomaly in a single day's query volume. Investigate first. Intervention only if the signal persists across multiple monitoring cycles. Number 2, a severe drift signal or a critical quality status warrants immediate intervention. The pipeline is operating outside its validated envelope. The appropriate response depends on the root cause. Input drift that reflects a genuine shift in user needs requires corpus expansion and baseline recalibration. Retrieval drift following corpus ingestion may require retuning the similarity threshold. Response quality decline following a model update requires rolling back to the previous adapter version while the new version is evaluated. Number 3, an infrastructure alert warrants immediate operational response. High GPU memory utilization that is not resolved by reducing current request load indicates a hardware capacity problem. Sustained high latency that is not correlated with queue depth indicates a serving configuration problem. Error rates above thresholds indicate a pipeline component failure that requires log inspection to localize. Section 6. Recalibrating the baseline. The quality baseline from Part 19 is not permanent. As the pipeline matures, the corpus grows, and the user behavior stabilizes into consistent patterns. The baseline should be recalibrated to reflect the pipeline's current normal operating state rather than its initial deployment state. Recalibration means running the full evaluation suite from Part 19 against the current pipeline state and generating new quality baseline JSON with updated thresholds. Recalibrate when the corpus has grown by more than 20% since the last baseline, when a new model adapter has been deployed and validated in production, or when the monitoring infrastructure has been running long enough to establish that current metric levels represent genuine normal operation rather than post-deployment settling. Every recalibration should be logged with the conditions that triggered it. A baseline history that records why each recalibration occurred is the audit trail that makes the pipeline's evolution reconstructible. Section 7, what comes next? The monitoring infrastructure is in place. The pipeline is deployed, tested, and watched. One article remains. The capstone ties every layer built across this arc into a single operational narrative, showing this complete system from raw NOAA data to monitor and production inference, the way it works when everything works together.